Dear students, I welcome you in this lecture on functional analysis. We will study finite dimensional spectral theory. This is the last chapter in the syllabus. In this lecture, we will study eigenvalues and eigenvectors of linear operators. Let us study eigenvalues and eigenvectors. Let T be an operator on Hilbert space H. A scalar lambda is called eigenvalue of operator T if there is a non-zero vector x in H such that Tx is equal to lambda x. Tx is equal to lambda x. If lambda is an eigenvalue of T, then any non-zero vector x in H such that Tx is equal to lambda x is called an eigenvector of T belonging to the eigenvalue lambda. Sometimes eigenvalues are also called characteristic value or proper value or spectral value, and eigenvectors are called characteristic vectors, proper vectors, or also called as spectral vectors. The set of all eigenvalues of T is called spectrum of T and it is denoted by sigma T. So let us briefly revise the concepts which we have seen. What is eigenvalue? Eigenvalue of linear operator T is a value of the form Tx is equal to lambda x, where T is an operator on linear space or vector space V to V. The lambda is called eigenvalue of T. Here there is x is non-zero vector, so x is not equal to 0. Vector x is called eigenvalue. Vector x is called eigenvalue corresponding to eigenvector lambda. Eigenvalues are also called as spectral values. Eigenvalues are also called as spectral values. So they are equivalent terms. Eigenvalues are same as spectral values. Sigma T denotes the set of all eigenvalues of T. So set of all lambda such that lambda is eigenvalue of T. Lambda is eigenvalue of T. let us come back to the notes. So, the set of all eigenvalues of T is called spectrum of T and it is denoted by sigma T. Note that if Hilbert space H has no non-zero vectors, then T cannot have eigen vectors. In this case, there is no theory can be developed. Therefore, throughout this chapter, we shall assume that Hilbert space H is non-zero. Let us see the theorem. If X is an eigenvector of T corresponding to the eigenvalue lambda, then alpha X is also an eigenvector of T. So in other words, any scalar multiple of eigenvector is again an eigenvector. So any scalar multiple of eigenvector is again an eigenvector. So any scalar multiple is again eigenvector. This easily follows from the fact that T of alpha x equals to, so it is easy to observe the sequence of equalities T of alpha x equals to alpha tx, which equals to alpha times lambda x, because x is an eigenvalue corresponding to lambda. What is x? It is an eigenvalue corresponding vector to lambda is x. So alpha lambda x we can write it as lambda alpha x, which actually equals to lambda alpha x. So thus what we have, T of alpha x equals to lambda times alpha x. Thus any scalar multiple of eigenvalue is again any scalar multiple of eigenvector is again an eigenvector. Next theorem, if x is an eigenvector of T, if x is an eigenvector of T, then x cannot correspond to more than one eigenvalue of T. X cannot correspond to more than one eigenvalue of T. So here we have two eigenvalues, say lambda 1 and lambda 2, to which x corresponds. Then we will have Tx is equal to lambda 1x and Tx is equal to lambda 2x. Then lambda 1x will be equal to lambda 2x because both lambda 1x and lambda 2x equals to Tx. This implies that x into lambda 1 minus lambda 2 equals to 0, and this further implies that lambda 1 is equal to lambda 2. So x cannot correspond to two distinct eigenvalues of t. If it corresponds to say lambda 1 and lambda 2, where lambda 1 and lambda 2 are eigenvalues, then lambda 1 must be equal to lambda 2. Let us go through next result. Let lambda be an eigenvalue of operator T on Hilbert space H. If m lambda is the set of consisting of all eigenvectors of T which corresponds to the eigenvalue lambda together with vector 0, then m lambda is a non-zero closed linear subspace of H, and it is invariant under T. The space m lambda is also called as an eigenspace of T corresponding to the eigenvalue lambda. So let me define what is m lambda. We will see what is the space m lambda. It is the eigenspace, means m lambda is the set of all eigenvectors corresponding to eigenvalue lambda, set of all eigenvectors corresponding to eigenvalue lambda. Now this m lambda is called eigenspace, and it is the linear subspace of H which is invariant under T. An immediate question which may arise is that, does an arbitrary operator T on Hilbert space H have an eigenvalue? The answer is no. For example, consider the operator T on L2 defined by T, the sequence x1 x2 gets mapped to the sequence 0 x2 x1 x2, so it gets mapped to this sequence. Lambda is eigenvalue of T, and if we have Ty is equal to lambda y, then T of the sequence y1 y2 must correspond to lambda y1 y2. This will imply that lambda y1 must be equal to 0, lambda y2 must be equal to y1, and so on. Since y1 is non-zero vector, y2 is non-zero vector, or at least one of them is non-zero vector, we can say that lambda must be 0. So T cannot have any eigenvalue. In this lecture, we defined eigenvalue, eigenvector and eigenspace of linear operator on Hilbert space. In next lecture, we will see few more concepts. Thank you.